or random vector, okay? But to take into account that random vector is from probability point of view and is a tool from modeling, okay? But for me, from statistics, I'm going to say statistics, okay? It's okay? Okay, then X is information, and this idea of this one from probability, you have to think it's this idea of a way to format the process, okay? The information is more general. It's interesting from science, from engineering, and etc. And this idea of information, if you say, if I am thinking in physics applications or in engineering applications, for X maybe is representing some object, abstract object. Then maybe are numbers, no? Is the more easy. For instance, counts, frequency of something, but continuous measure, etc. But time series is included in the sense to represent this one as an object where the time is present, okay? And moreover, an image, okay? An image is another abstract object that I want to show as information, or a frame, a set of frames, no, like a video or something. But from engineering, physics, and etc., more applied science, X is information provided by different objects. From a mathematical point of view, X is like a object, for instance, random vector, and you can see in some sense using the most classical notation in probability, X live in Rn. No, of course, X is from this point of view, it's a random variable or random vector, and this idea of include, you know, this one is a function measuring some events, etc. But we use this classical notation, and the most important is for us, X is embedded in Rn. Then, in general, information are different type of objects, but the main point is this idea that these objects are going to embed it in some Rn. Okay. Then for now, when I say X is information in general, in your mean time series, image, doesn't matter. And the most important to understand that from some different applications, it's interesting to consider this object embedded in some sense, in some way, in a Rn. Then in the moment when you fix this one, you are talking on this one. Then you can see that, for instance, with only one dimension, when you fix this embedding, you are fixed, for instance, the unit of the measure. Okay, it's the most easy case. You fix a unit, I am going to measure in meters, then you do embed it in R with this unit, and then this one is fixed, and the measure and the random variable is fixed. But this idea, or this main approach to relate information and random vector, is very important to put in your head. And I am going to use this scale of information, but in your mean, it's important you understand that when I say information, you have to be very clear that information is some object that is embedded, and as a result, you select a measure inside Rn. Okay, I put Rn, and in all examples, always I am going to relate with continuous measure. Okay, from probability, I am going to show continuous measure. Moreover, absolute continuous measure. Okay, why? Because another part, a strong part that you need to understand is, from probability point of view, when you analyze different type of measures, it's very interesting to analyze some particular case where some results are strong, or let to show some other examples or etc. But in the world or applications or this idea of information, this embedding is easy because really so there are some cases and small examples really where you need to consider more than this, okay? Then with the more easy approach where your measure is the typical one, it's enough to introduce all concepts. Of course, when I say X, you have to be thinking in information. Of course, you have to be thinking that it's going from probability, from measure. And of course, you are to be able to change this strong property if you need. Okay, but now you can see I am going to relax the notation because all the time I say X information and I am going to use strong properties because really in the real time, in the real world, this is the most typical case. Okay, then I am going. This one is you me. I forget for me because I need the blackboard, but now only this one information. Okay, but I am going to remember. I am going to remember that this information is like a random variable, no? Then let me to show in one dimension because it's the most easy one. Suppose that you have one dimension only, and x1 is a random variable. Sorry, I put in Catalan, random variable. I have only one dimension, and in the most easy case, I am going to use a notation F for PDF, the probability density function, F, capital letter for complementary distribution function, okay, with the property of F point X is equal to the probability of X is less than X, and I can obtain this one with the integral of Ft, okay? Then, you know, this is an approach, it's a general approach, and I suppose X is in F. But I am going to fix that I can do everything abstract, okay? When I need to use discrete measure, I am going to remark different cases. But I think with only 4 hours, I cannot explain more details on this particular case, okay? But this one is the most interesting in order to introduce the role of statistics in machine learning, because really the most important models in statistics that are very useful today in machine learning are related with neural networks, okay? Then now in this part, I am going to, if you want, this one is an introduction on statistics point of view. And let me show some details on machine learning and artificial intelligence, okay? Now, I want to talk on machine learning and artificial intelligence. Maybe you know a lot of results and you know several definitions for every one of them. From my statistics point of view, when you want to relate how statistics contribute to these disciplines, it's very important to remark that these concepts from mathematical point of view, okay? Then, for now, we forget statistics, and we are going to talk on artificial intelligence and machine learning, okay? Artificial intelligence, for now, for us, from mathematical point of view, is several tools or different applications that led to construct some algorithms for to do something automatically, okay? It's the idea of to be thinking, but with a machine, or to be learning, no? In artificial intelligence, really, because there is not too much clear. Artificial intelligence include all that you know. Robotics, the main one, because this one includes hardware plus software in the most expensive point of view. Machine learning is more related with software development, okay? However, includes hardware, but hardware developed in machine learning is more related with computing resource, okay? where is mathematics in this process? Of course, mathematics is in all the parts, no? Because in Howard, for instance, in design, mathematics, so but is not the part that we are interested, because we want to see which is the math approach to relate with statistics. Then I am going to forget statistics in hardware design and etc. And always I am going to fix in this one. Okay, when machine want to learn, need to develop software, and this software are going to include no statistics, are going to include data. Okay, this is a particular case when I am going to put the focus. Remark that really mathematics is in every part exists mathematics, but the talks are going to focus in this part. Okay, when machine learning as a part of the developed software in artificial intelligence include results based on data. Okay, this is in some sense a very easy approach in order to understand exactly where statistics need to strong develop, because really the statistics are going to put a part where you need data in order to understand what you have to do for to learning. Okay, you can see data because everybody says data, but for us, this is the joint point. Data is information, is this X. Okay, the machine learning process uses information and learn. Information many times is taken as a data, but remark that really data, this information is a lot of different objects, but from mathematical point of view, you can see like a random variable, but maybe it's not necessary. Maybe this data can be thinking with X, no random variable, X like a set of points or points in Rn, for instance. If this one is inside Rn, then it's a set of points in Rn. Okay. Then, from mathematical point of view, exist two types of machine learning. Really, another type, but there are another main important one, but it's related with these two types. Then I'm going to focus on this one. One is supervised learning and non-supervised. When I say supervised learning or no supervised learning, which is the difference from mathematical point of view? The difference is easy because learning is when you use X information if you want data, okay? Because for now, no, I am not going to suppose a stochastic pattern, okay? Data is some data that I observe, but it's not necessary that exists a stochastic pattern. It's not necessary to be thinking in probability. Then when I say I have data and I learn, from mathematical point of view is I have X and I learn something. This is that I learn, okay? I observe, I have some X and I want to learn another one. Then I want to put a row, X produce learn. X, some data, produce some result. From mathematical point of view, this is to be looking for a function, or sorry, I am going to put this one for now. I am going to look for a function, okay? This is supervised. Supervised is when I have some information or data. Remark, it's not necessary to be thinking in a stochastic pattern, and I am looking for a F. And my question is, who is F? Who is F? F, in order to connect this that I observe with this that I am going to learn or I need to know. Non-supervised is more or less the same, but now I observe X and I don't know which is the path for learn, but I need to extract information, extract some knowledge. Then I am looking for a F, equally, I am looking for a F, but now F are going to produce knowledge. But the knowledge, the final object of knowledge, I don't know. I only want to know which is the way when I can reduce a strong set of data or a strong observation in a most reduced set of knowledge. Of course, a lot of data, a lot of knowledge, if I can reduce in some sense with some F, all this knowledge in a small set of observation of data or objects, then I get to do a non-supervised machine learning, okay? The idea of reduce, non-supervised, and the idea of to construct is supervised. This difference really from a mathematical point of view is not too much because I am looking for it always, okay? Remark that this point of view is based on F a function without constraints, and moreover, X with not necessarily stochastic pattern. Okay, this is an important point because from a mathematical point of view, you can develop this problem without stochastic pattern, and you can solve many problems in machine learning without probability. Because there are several problems in physics, for instance, when you can produce some data as a simulation of some strong differential equation, for instance, and then you are looking for some solution, then you really the stochastic pattern, maybe it's necessary because you need to do some simulations and you need to introduce some stochastic process inside, but maybe you know from theoretical results that you are going to look for, or you can get a deterministic result, okay? F can be deterministic. Then in this point, you can decide if you want to introduce some stochastic pattern or not, okay? Then when you decide to put a stochastic component, of course, you are going to consider X as a random vector, and we are in this part, okay? The main result in mathematics, now very, very short, the main results in this part from only mathematics, from deterministic, are very interesting because there are several results that showing the existence of good solutions for several problems. However, from practical point of view, when many times you cannot sure about some hypothesis on the F function, you need to consider stochastic. I want to say, maybe your problem is clear that you don't have stochastic pattern. Maybe it's very clear, but you decide to put stochastic pattern, a small component, okay? This is a decision that you can put, and in this part, you can see when I put this one stochastic, then F maybe is not exactly, is not the deterministic solution, but you are going to do some very good approximation of the result. Then you can see, I am going to fix in this one, because really, from a mathematical point of view, you are looking for it. Then this is the case supervised where you can collect the most important points of the process. When you do this one, maybe for you it's clear that you can do some things, for instance, approximation with several numerical methods. You have some point X and you want to fix the F, for instance, quadratic or I don't know, and then you can compute the error, no? Then this one is, the result with this one is dual, the results of to put this error in the form of uncertainty of probability measures, okay? Then let me to show some things on probability measures. The most, and now I think to show my screen, one moment. Let me to put, I cannot see whether I can put. Okay. Okay. With this that I was explaining, you can see I put very clear that some sense of measure of uncertainty, no, is from a statistic. Then I am going to cover the part of machine learning, but first, today, I think it's important to fix some notation and some ideas on measure uncertainty, okay? Really, from machine learning requirements, you need to be working with very strong data sets and know a lot of variables, a higher dimension, but moreover, complex, for instance, complex complex process for to obtain and different ways for to measure the results, okay? Then now from I check, now you put this one in your mean, and of course this is very important for machine learning, and I am going to come back, but now easy, only preliminaries, the main points. You can see when you have a lot of things. Okay, this one is a small detail. You remember when I put F, this that I say F is the probability density function. With this one, I can compute the probability. No? See?
The screen didn't change.
Huh? You can, no? No change?
No, it's frozen.
I don't know why. Okay, I am going to start again. Okay. Now?
Yes.
Yes? Okay. That I want to fix this one, F, because I am going to use probability density function, but now the most important is to introduce this one, theta. You can see theta, X is the random variable, of course, is the value of the random variable, but theta is the standard notation, and I want to fix the parameters of the law. Very important from probability point of view. F is a probability density function, no? Then the probability density function is a positive function, of course, and in the full range of the random variable is 1 because measure the probability, no? But very, very important, theta, this one is fixed, is known. In probability, theta is fixed because it's known. If it's not known, if theta is unknown, then it's not a probability, it's not a law, it's a model, okay? Then, for instance, the most easy, no, for you is the normal or Gaussian distribution. You know, this is the probability density function. When I put this one, you can see X is a random variable, and this one are the different parameters, no, that you know, and this is the expression. Okay, then it's important to understand the difference between probability and statistics. Okay, and the difference is probability, this one is a function, and this one are known parameters, known. In statistics, this one is a family. It's a family because parameters are unknown. Okay, then when I am doing statistics, the main goal is to use X in order to infer in this one. Okay, statistics try to use information X for to infer in the parameters. Okay, then you can put as an example, thinking that if you say some population or some measure of this population, you can consider a normal law is not correct. Because if you say is normal, is a normal law for some measure, then you have to know exactly which is the parameters. But you can say, I am going to suppose that this measure is a normal model. Okay, and then when you say model, is because you don't know the parameters and you are going to use some information in order to infer in this one. Okay, then this is the main difference between probability and statistics. The known, for instance, known parameters or don't know, but the most important, more general, because this is a very easy example because normal distribution, everybody knows, but this one you can see is an example of parametric model because you can, it's a parametric model because it's a model of uncertainty that you can describe with parameters. Okay, it's a model of uncertainty that you can describe with parameters. This is a parameter model. Okay, but exists non-parametric model, for instance. Okay. Another example, for instance, for you is binomial. You know binomial, and it's very useful in many cases, but again, binomial, you know from probability calculation. It's a typical example for probability calculation. And probability calculation in I don't know, for instance, the typical example that I have some red balls and black balls, and you have to take something and how many, which is the probability such that you obtain 3 red balls, and these typical examples correspond to probability calculation, okay? But from statistics, this parameter is unknown. Then when you don't know this probability, this parameter, this one is a binomial model, okay? Poisson is very useful too from different physical challenge. And again, Poisson distribution is from probability. Poisson model is when you don't know this parameter and you need to observe several cases in order to infer in this parameter, okay? Then you can see in statistics, you have some functions with several variables, if you want, and some of them are subject to a stochastic process, and other ones are parameters. In probability, these ones you know, and this one you need to compute some properties, if you want. And in statistics, you observe and you need to know, okay? There are only some examples in order to show that, only for remark, this is the normal distribution and remark, no? You know, for instance, this parameter is going to consider where is the translation parameter, and this one is this one. Okay, for instance, when is bigger, for instance, this one equal to 1 is a more expand one, no? Every one of them, you can see, is that this example, this picture shows this idea of uncertainty. If I have some data, if you say, this measure, I can consider a normal model, okay. And now I observe one value. I observe something, I do a measure, only one measure, I can observe. Then, for instance, suppose my first measure is, for instance, -4. -4, then I suppose, the common sense say, if only one measure and it's -4, maybe it's not the green, maybe it's this one or this one, I don't know. The second measure, and I see, and when you obtain several measures, then you can infer which of them is more probable that you have. Then every time that you observe 1x, you are going to reduce the space of parameters. The first, this one is real, and this one is positive, but no restriction. Every time that you observe something, you are going to reduce the space of parameters. In this point, I want to recommend to use R, because I like to use R, but really Python is very good too. I don't know if you have some preference, but for now, in the next class, I am going to use R. But let me to show this one is a function with R. And it's interesting because you can see binomial, no? Binomial distribution. When I put binom, R know that I want to use binom model because R, the program, is not considering probability laws. Always consider models, statistic models, okay? Then when I put binom, the program is waiting that I say which is the parameters or to give some data or to do, okay? This is an easy example only to show, like, and to remember you that binomial and Gaussian model are very close, no? But the main difference, you can see, really this pattern, symmetric, and with this flexibility of patterns from translation, you can obtain with binomial distribution too. The difference, the main difference, of course, binomial is discrete and normal distribution is continuous. However, you know that exists, I don't know if you know, I say you know, I suppose, but binomial distribution is very close to the normal distribution. And we have a strong result, a theorem from mathematics with this approximation from probability result. But it's interesting to fix that when you are doing a statistic, you don't know if it's binomial or normal. From statistics, many times you have to assume or to do some hypothesis about the model, okay? And many times you cannot do any hypothesis on the model, and then you decide to search with different models at the best solution. Let me to show some parametric models additional, because I show Gaussian, binomial, and Poisson, because they are the more typical ones. But in statistics, there are some of ones that are very important too. And really, from probability point of view, many times are interesting examples, but from a statistical point of view, are very strong, have very strong application. One of them is gamma, and the reason gamma distribution, if you don't know, can be obtained when you are doing the sum of exponential distribution. Exponential distribution is very useful from physical problems. Then gamma appear from natural way when you want to do several different stochastic processes in some, for instance, differential equation. Pareto distribution is very important too, because many times in some strong systems, moreover, in complex systems, appear patterns, complex patterns related with the interaction of the individuals, and then the pattern, the events that mainly with binomial pattern or exponential or Poisson pattern are going to produce extreme events. In this case, when we produce extreme events, then this is very related with this model. The distribution, the Pareto distribution show the most easy model for modeling extreme events. Then I show these both of them, but really exist a lot of ones. And I want to remark that I show only parametric models, okay? I am all the time I am showing different probability density function, okay, from random variables, such that the uncertainty pattern can be described with parameters. It's very important that this idea that the uncertainty is described with parameters, because moreover, it's described with a finite number of parameters. And it's interesting to be thinking for 1 minute, which is the main idea in statistics of that. You can suppose idyllic example. Suppose that you have 1 million of data of something, and suppose that you can consider a gamma model. Then, if you have some evidence to use gamma model, and you can suppose that, then you only need to compute 2 parameters. And if you fix for a moment, if I have 1 million of data, a lot of data for X, and I only need to know 2 in here, then it's interesting from reduce information, because 1 million or 10 million, I don't remember what I said. This is a lot of information with only 2 numbers will be enough to describe the uncertainty. Then you can remove 1 million of points of data in your memory and to put only 3 things. Say gamma model, and you say alpha and this one, the 2 parameters. With you fix which is a model and the parameters, it's enough. You can remove. You don't need to save, or you put in your memory 1 million of numbers. Okay. Of course, it's a very beautiful example from practical point of view. Many times you cannot remove 1 million of data, but really this is the idea, produce strong results in memory reduction. In here, I remark, for instance, if you want to show some of one, there are some packages in R that you can explore. I don't know if you work on R. I am going to ask Stefanella for the next day to talk more, because maybe if you want, I can do some small introduction of R previous to show examples.
Yes, yes.
Yes, okay. Then in the next class, I'm going to do a small course of R, enough for modeling. really R is very easy. It's like a calculator. It's not, you can do strong things, but I am going to show the small ones for to do these first steps in modeling, okay? Okay, gamma, let me to show the gamma, because if you don't know gamma, this one, this is important because it's very different of normal, no? Because include exponential, the green, but with a different patterns and different shapes that you can see are not symmetric, etc. Then from modeling point of view, gamma is more flexible than normal distribution when you need symmetry and etc. Okay. Fixed notation. Oh, okay. Sorry. Fixed notation. Now, when I say sample, sorry, because it's in Catalan. I was thinking I am going to talk in Spanish, then it's not too much different, but now in English, it's really different. But maybe I can translate because really there are not too much text. If you need the slides, let me know. But this one sample, okay? Sample, when I say sample, many times I am going to put X with this one or with a bold, but bold is so different. Many times it's not easy to see. And it's a set of observation, okay? When I say I want to choose a model is this one, is to be thinking that the probability density functions, but a set, because theta is unknown. I don't know the parameter, then it's not only one function, it's a set of functions. Another important notation is this one. You can see I put a hat. The idea is theta is we say it's a population parameter. And I am not going to know never, because I can increase the sample. Okay, I'm going to, maybe I can get a lot of sample and to be increased n, but never will be enough in order to say that you really know which is the parameter theta. The main point in probability, the main point in statistics from probability results is this idea that if you suppose a stochastic process, then never will be enough the data that you observe for to fix exactly which is the parameter theta. Then, if you cannot fix which is the parameter theta, that you can do is do some approximation. And in statistics, a typical notation is put a hat. When I put hat, it's because I put some number that try to approximate theta. But theta is never known, okay? But my main goal will be take some n observation and to give you some theta hat, okay? When I say theta hat, I say it's a punctual estimation, okay? The main keyword is punctual because I show a point. I put a number for theta. Remark that theta can be a vector of parameters. For instance, in Gaussian model, you have two, mu and sigma. Then, of course, theta hat is a hat of a vector of two components, okay? But in any case, it's a point in a space. Then it's punctual estimation. Estimation is a very important keyword because when I say estimation is because I am considering I have a sample, and moreover, I am considering that I am doing a stochastic approximation. Because remark that if I have this problem, if you fix this problem, I have some points. I need to fix, I have a set of F, and I need to know theta. Again, you can do from numerical procedures some solution. Always you can do it from numerical procedures with, for instance, with less squares. And this is a good solution. But when you are doing this one, you are working on results from analysis, and you are going to measure with an error. This error is measured with some properties on the function. You are going to do some derivative and etc. Really, in statistics, I am going to do something like this, but the derivation of the error is based on some model for the error. Then you need to say estimation, no approximation, okay? Approximation, when I say the goal is, of course, approximate, but you can approximate from analysis or from statistics. When you approximate from statistics, you say estimation, okay? You can see in the future that really are very close, both approach, but different assumptions, okay? Another way for estimation is not punctual, is using uncertainty. Because you can suppose that you observe only one, of course, you can produce some estimation of the parameter, but maybe it's not too much good. When you have a lot of observation, the common sense say that you are going to get a better value for theta, no? Then theta hat maybe is going to be improved when you increase the sample. This is the common sense idea. Not always, this is the common sense, but there are some different cases that you have to consider. But for now, I am going to use common sense and use this idea. Is obvious that you can introduce some idea of interval, okay? And you say, okay, theta, I don't know who is, but when I estimate one number, can be improved estimating two numbers and say, okay, theta, I don't know, but live between this one and this one. Then you can do punctual estimation or an interval estimation, okay? For instance, in the previous example, I say, if I observe -4, -5, -3, maybe mu, the mean is not 10. Then I reduce really, and maybe I don't need to put exactly a number for mu, but I can put an interval, okay? Then estimation punctual, interval estimation, okay? When you consider interval estimation, it's interesting to put some probability to live in this interval, okay? I am going to talk with more detail with this probability to live in an interval, but now only fix the notation. When I say an interval where live the parameter, I can use alpha to remark the probability that theta don't live in the parameter, okay? Or the same, 1 minus alpha is the probability that theta really live between these numbers. And the common sense that I was explaining is if n is going to, if n increase, then the confidence, 1 minus alpha, the confidence that theta live in these between two numbers are going to increase too, no? Because you are going to reduce the risk. You increase information, reduce alpha is the risk, and increase the confidence, okay? Okay, this is the main keywords that maybe you need to know and you remember, because I am going to use all the time. Remark, sample, model, estimation, punctual estimation, put hat, interval approximation or interval, uncertainty measure for the parameter. This part is strong, and I am going to only introduce some main topics, okay? This one is an example that I was thinking is interesting to be thinking, because I suppose, but I don't know, but I suppose that everybody knows how to solve a problem related with a normal distribution. You don't need to read now the slide, only listen. So only if you want, you see these numbers, okay? Suppose that you have a sample and observe these numbers, okay? It's not important, only an example. And observe the numbers, and I say, suppose that you have a normal model. If you suppose a normal model, no? Then you need to search mu and sigma, the parameters. And I don't know, but maybe I suppose that everybody knows, but now you can be thinking in that. But if you need to know the parameters, you are going to do the mean and the standard deviation. The mean is the best way. I am going to say the best way, but best is really with a strong justified. But now only say best. Mean is the best way to fit mu, and standard deviation to fit the sigma. I don't know if it's very easy for you, but I am going to show this case with a lot of details because the statistic theory is more general, but the particular case of normal is very important to understand, because when you understand the normal case, then it's easy to understand that normal is an example of a different of a parametric model, but really you can extend the result. Okay. But when you do inference, this idea of to compute mu and sigma and to put, no, I can put mu hat using the mean of the sample and sigma hat using the standard deviation. Okay, and I can do a confidence interval. Exist several books talking on that, and Wikipedia, a lot of places you can see how to do it because it's a most easy and more extended case. But when you do inference and you are working in more complex problems, no, like you can see in machine learning, you need to be thinking in more strong assumptions, not only model, but in this slide, I put some examples, but information, when I say information, is all that you know on the data. Then, for instance, if I know that the data is truncated in 1 decimal, then I can improve my model. Okay, that I say this one can be modeled with a normal, but if somebody say, be careful because the data is truncated with 1 decimal, then really the data that I observe is not normal because it's a normal with 1 decimal truncated. Or if you say, be careful because this data that you observe is not considering numbers slower than 3, for instance. You can see the small one is 3.2. Suppose that somebody say, be careful because this data is not including numbers like 1, 2, because cannot be observed. I only can observe numbers bigger than 3. Then, of course, you can say my observations from a normal distribution or from a normal model. I can say, but be careful because numbers lower than 3 are not observed. Then really, the classical normal model is not useful. I need to describe a truncated normal model, okay? Because I have to describe which is really the pattern of uncertainty of a normal model when the numbers, when I observe only numbers bigger than 3 and where observe numbers truncated with 1 decimal, no? Then I can put a lot of examples where you can see that when you are working in statistics, you need to be careful with this lot of assumptions because really modify the model. Maybe for you, normal model, it's okay, but the data not produce precision or loss some cases or etc. Then the uncertainty that you observe is not the uncertainty that you suppose. Then you need to change the model, okay? This is an easy example and really artificial, but very close of a lot of real cases. Moreover, when you suppose that you let to describe an uncertainty model with its properties, somebody can say, no, I need to remove. Are not normal. I think I model gamma because maybe when you observe the data, you decide that symmetry is not a good assumption. Then you need to change the model normal for a model gamma. And then you need to take the uncertainty described from a gamma model, introduce again that you are not going to observe values less than 3. You need to introduce that the numbers with some truncation, and it is okay. I don't know if it's more or less clear. I think maybe as is rated in Catalan, maybe it's not very useful for you, but really you don't need to do the exercise. But it's important to understand which is the capabilities.
Portuguese is very understandable.
Okay. Great. But then really is this idea that if you understand and you can try to do the exercise, it's fantastic. But the most important is to be thinking that probability led to describe laws, and statistic led to take a family of laws in order to put a parametric model. Parametric model is very useful because with some parameters, I can summarize all or a very large data set with a very strong pattern of uncertainty. But in real cases, I have to take into account that the models from probability are very beautiful, but many times are not useful because I have to include several constraints like these ones, okay? And moreover, normal distribution appear in a lot of cases, but really the model in many cases are more close gamma than normal, okay? Okay, the next part, I was thinking to start the next day, but I have a minute, maybe 1 minute. Stefanella? Hi,
Hi.
I have 1 minute or 2 minutes.
Yes. 1 minute. Yes, of course.
Yes, okay. Only this one to show very quick. The main point for the next day is this idea of to estimate parameters, okay? Only show this slide because it's a good summarize. Okay. The main part you can see is to translate uncertainty of observation in uncertainty of parameters. Then this is the most important point for now. Uncertainty of observation in uncertainty of parameters, or uncertainty of information in a estimation, a punctual estimation. Then the main method to do this one is least squares. Least squares from Gauss, and really this one is related with analytical results, okay, based on numerical procedures. But when I say least squares, there are many important points. It's the most classical one, but really, when you do least squares, in some sense, in your mean, it's very clear that you are considering Euclidean measure in Rn, and it is not necessary in statistics, okay? Then least squares is the most classical one and is related with a strong results from mathematics, but this one suppose that the error have to be measured with L2 measure, okay? Then this is okay many times, yes, but the statistic approach is not fixed the measure of the space. The statistic approach fixes the measure if you have some information for to do it, okay? But the first one, of course, is to fix L2 measure, okay? Different methods for to do estimation where the measure of the space that you suppose, the measure of the error in Rn, where is the data, is not necessary to be included. A pair with Pearson is a method of moments, and Fisher, more actual, is based on likelihood, maximum likelihood estimation, okay? Then blue are the main ones, and I am going to show some details. The first one from Pearson and the other one from Fisher, okay? And more actual now, but only this is very, very young, you can see, is the Bayesian estimation. Now this one is very important and really is very classical one, but you need really a strong computational resource for to do it. And now, some years ago, this one is available because you have several resource in your computer, for instance, and you can do this one. Of course, exist a lot of other methods, okay? Then you can see, I want to finish. You can see if I have several methods in your mean, maybe you are thinking, oh, if I have several methods to estimate the parameters, I need some criterion to decide what I have to do or which result is better. Because when I have some data, if I try to fit some parameter with this one or the other one, the result is different. Every one of them, for instance, are going to produce different point estimation. Then you need to decide which is the better. And in order to decide this one, we need some properties on the methods of estimation, okay? Then this part, I am not going to explain too much because I prefer to relate these first results with machine learning. But if you are interested, when finished, let me know, okay? Maybe I put in here and the next day I can comment something else, but Newton-Raphson is the most typical one algorithm because at the end there are several methods to describe how to do it, but at the end always, or always maybe no, but the most of the cases, you have an optimization problem, a hard optimization problem, okay? Newton-Raphson solved the most of them, but now EM algorithms, expectation maximization algorithms, are very useful to solve the main problems in this part, because these ones produce methods to do it, but at the end you need numerical procedures to compute really, okay? Okay, for me today we can finish, but let me know if you have some questions or comments and you need something.
So first, let's thank Isabella. We had to change room because we had a technical problem. So I think that they can mark the question if you can send us some material eventually, something that I can read ahead of time, maybe also for the next class. So
Okay.
Yes?
Yes.
You have a question? No, not yet. But Catalan is closer to Portuguese, so they can they can read the. I think Catalan is closer than Spanish to Portuguese, so they can.
No, really.
Yes.
I was thinking we can do some. I want to introduce some main details, and I have a different course that I do more extensive. Then in this one is in Catalan, but for instance, my notes on neural networks are in English. But if it's okay.
Yes, it's okay. Yes. Yes,
Okay.
great.
Thank you very much.
Thank you very much for. It's an honor to have us with you up to Brazil. We hope next time in person. In the future. Okay.
Yes,
Thank you very much. Thank you.